healthcare policy at Harvard Medical School. Laura is also the winner of the 2018 SCORE Health, Economics, and Outcomes Research Methodology Award. And
thank you. Good afternoon. Pleased to be here. Before I start, I want to say that although I'm the person up on stage, this work is the product of thinking by a whole bunch of smart people who are pictured here. And also, I want to thank the funders, both an Institute of Health and the Laura and John Arnold Foundation. So I'm a policy researcher by practice, although I'm a biostatistician by training. And that means that part of my job is to evaluate policy ideas that policymakers out in the world have. And because I'm in healthcare policy particularly, a lot of the questions that we answer are about policy ideas that are designed to improve quality and reduce costs and improve outcomes in care. So things like bundling payments together, changing prescribing laws, putting prescribers on a budget, and expanding insurance coverage are some of the ideas that get evaluated by policy researchers like myself. And importantly, almost never do we get the chance to do a randomized trial. So we never get to design an experiment. We almost never design the data collection mechanisms. We're stuck with the ideas that the policymakers had and the data that are routinely collected in practice. And so that makes our job a little bit harder because we are really truly interested in causal inference, but we don't get to design experiments. So we have to work a little bit harder to come to our conclusions. And one way that people have been frequently able to evaluate these policy ideas that are out in the world without having had the opportunity to design a study is the use of something called difference in differences. So before I go through the boring details of that, let me first make sure that I understand who here is familiar with difference in difference. So raise your hand if you've read or relied on a diff and diff study before. Oh, awesome. This is a group of newbies. So have you ever done a difference in difference among those few? Okay, a few hands. So this is great. I love a fresh audience. So a diff and diff relies on observations of a group that will have the intervention applied to it, the treated group, and a control group before the intervention and after the intervention. And remember I said that we're using routinely collected data, which is why we have data on untreated and treated people before they ever get treated. Then the intervention occurs, and we get to observe them again after the treatment has been applied to one of the two groups. And then we observe the change in the outcomes. Now, crucially, the change in the outcomes of the control group is what would have happened in the absence of intervention to that group, right, because they didn't get the intervention. And we use that as a counterfactual for what would have happened in the absence of intervention to the treated group had they not received the intervention. And by comparing that counterfactual change in outcomes to the actual change in outcomes of the treated group, we can estimate the causal impact of the intervention on the treated group. And usually what we're estimated, the estimate of interest here is the average effect of treatment on the treated, not the average treatment effect for the causal inference nerds in the crowd. So this design is really popular, it's really useful, and it relies super crucially on this very strong assumption, as all causal inference problems do, right? We rely on strong assumptions, especially in the absence of randomization. So our assumption, and I'm stating it in this kind of wordy way, because I think it's super important to say this clearly, that the change from pre to post intervention in the control group, the unaffected group, is a valid counterfactual for the change that would have occurred in the treated group had they not gotten the intervention. Another way to say this is that the difference between the two groups would have remained constant had the intervention not occurred. And the reason I like to use the word counterfactual in this assumption is because it reminds us that this is an assumption. We can never test this because doing so would involve observing outcomes that did not occur. Okay, so we're stuck with this. Despite that, I love that every time someone searches for something in PubMed, it's exponentially growing. So, surprise, diff and diff is exponentially growing in PubMed. It turns out it's because everything is exponentially growing in PubMed. There's just exponentially growing articles in PubMed. Diff and diff is no different. I will say, however, so this is the last 20 years. Fun fact about exponential growth, it doesn't matter what time period you look at, it'll always look like that. The methods work has really lagged. So these are applied papers for the most part. Throughout my talk, I'm going to have a lot of cites of methods papers, and they are primarily working papers and in progress and to appear. So the methods work has just started to take off in the last few years, and the most of it is happening in economics literature. The econ literature, contra medical research, has a very long latency during which the papers are working papers that are being shopped around. So those can spend 2 or 3 years in the working paper phase before they ever hit the journals. So that's part of the reason. Here's an example of the kind of policy analysis for which people would like to use difference in difference designs. So the Affordable Care Act in the United States was passed, and it was meant to expand the eligibility for Medicaid, which is the federal insurance program that covers people who are low income, disabled, and in nursing homes long term. That's a federal state partnership. And Congress passed the law saying we would like to expand eligibility to people who are making people who don't have children and aren't disabled up to 138% of the federal poverty limit. That's actually an extremely low income limit. However, the Supreme Court said, actually, the federal government can't tell the states to do that because the states are partners in this program, right? So each state gets to make up its own mind whether it wants to take this federal money and expand eligibility to cover more people in their own state. And every state made its own decision about whether or not to expand eligibility to 138% of poverty. And they did so in an extremely politicized way. So if you know anything about the electoral maps from yesterday that we kept seeing, you will recognize that the places that did not expand are what are usually plotted in red on these maps, right? Those are Republican-leaning states. There are some exceptions, but for the most part, the places that elected not to expand are red states, and the blue states decided to expand. What this gives policy researchers like me is a bunch of little natural experiments, right? We have a bunch of states that expanded and a bunch of states that didn't. And so the obvious thing to do would be to call the treatment states, the expanding states, and the non-expanding states the control group and do a diff and diff study. So that's in fact what 203 people have done. This is a slide from the Henry J. Kaiser Family Foundation, and in fact, I think that number is outdated. Now it's 205 as of today. So many people have taken advantage of the series of little natural experiments on Medicaid expansion to do difference in difference analyses and find things like coverage gains. That's almost a tautology, that if you give people coverage, they will get coverage. Okay. Access to care, affordability, and reductions in uncompensated care costs are some of the more non-obvious policy goals and outcomes. So here's an example of the outcomes of one of those 202 studies. This one was published in JAMA a couple of years ago. This is a graph showing over time in 3 years prior to the expansion of Medicaid and 1 year post. So we've got 3 pre-years and 1 post-year. In states that did and did not expand Medicaid, this is the amount of care that is going, the amount of dollars, the dollars going to uncompensated care. So this is in the US, when a person arrives at the doors of the emergency department, they have to be treated and stabilized. And the hospital can try to collect the money that it costs them to treat that person, but eventually, if a person is unable to pay and doesn't have insurance that will cover it, they just write it off, take a loss. So in the states that expanded Medicaid, not really surprisingly, in 2014, after the expansion, the share of uncompensated care in those states went down. This is good for the hospitals because now they're getting paid for the care that they were delivering. And in the non-expanding states, you can see that it didn't happen. That was really easy to see, right? We could look at the graph with our eyeballs and we could tell exactly what was going on. When the lines are further apart, as they are in this graph, so this is the mean annual Medicaid revenue. You can notice a few things on this graph. First is that the expanding and the non-expanding states, the hospitals in those states, have dramatically different amounts of dollars, Medicaid dollars flowing to hospitals, right? Without Medicaid expansion, the amount of spending in those states on Medicaid is very low. Why is that? Is it because their people are so healthy and they just don't need any care? Well, remember back to the map, it was like Georgia and Alabama, and anyone who knows anything about the United States health map, the epidemiology maps, those are the sickest states. No, it's because they're stingy, right? They didn't expand Medicaid because they don't like spending public dollars on these public insurance programs. And so their state Medicaid programs are ungenerous. They don't cover very many people, they don't cover very much stuff, so they are really quite different states than the states that expanded. And remember back to that crucial counterfactual assumption. We are asking the non-expanding states to be stand-ins for what would have happened to the expanding states in the absence of expansion. And it's clear that in level, they are not at all stand-ins. But what's important is, are they stand-ins in trend? And that's all that matters, is would this difference between them, which is substantial, have maintained over time? It's also harder to see on a graph where the lines are quite separated from one another what's actually going on. So we can't just look at the graph and see whether there was an effect or not. We would need the lines to be closer together to see if there was a differential change. And what most people do is, at this point, we start writing down regression equations, right? We're not going to actually do this with lines on a graph.
Error bars, is there uncertainty in these?
Yeah, because I think these come from a model. Yeah, these are model results. I don't think these are actual dots. So I'm going to come back to that. Why would you put stuff in a model is one of the key questions that I want to talk about. But I think these are model results, not estimate uncertainty. Okay, so my research questions are broadly these four. And unfortunately, as I was writing the talk, even though I have this awesome 50 minutes, which I share Ruth's amazement at, I really can only get into two of them. So I'm going to talk about the first two, and then I'm going to tease the last two, because that's ongoing work. So our first two is, the first question is, should we match on pre-intervention variables? Remember, those states look really different from one another. And our intuition, and sometimes people call this face validity, is that we should compare like to like. So maybe there are hospitals in those non-expanding states that resemble the hospitals in the expanding states and vice versa. And perhaps we should form a sample where the things that we are comparing are more similar to one another on whatever stuff we can measure prior to the intervention, because that just feels right. And our intuition from cross-sectional studies is that like belongs with like, and we should make the samples more comparable to one another. So that's my first question that I'm going to talk about today. Here I've reproduced that graph using my own colors to illustrate that we might want to do some procedure that will take that gap and close it as much as possible. Now, this was the case where they were already pretty close together, so it's reasonable to believe that we could find hospitals in the two sets of states that are similar enough to one another that we could make the lines lie right on top of each other by selecting hospitals from the two groups of states that are comparable. And we could do that by matching on outcomes or covariates, right? Because we're talking about the pre-period, we can actually match on outcomes, which is a thing you would never do in a cross-sectional study, right? When you write down your propensity score model, outcomes are not involved. You're just looking at covariates. But here we could actually match on outcomes if we wanted. So what would happen if we did that? Well, most of the time people don't match on outcomes, but sometimes they do. And these pull quotes are from a variety of applied papers that I picked kind of at random from the literature to convince you that matching is a thing that people very frequently do in difference and difference design. And they are also very frequently a little vague about what they match on. But matching is a thing that is really common. And what I'm going to argue today is that the reason that the two groups differ from one another is crucially important in helping you decide whether you should match on stuff. Okay? So now I'm going to show you simulations. These are simulated data from a population where the treated and the control are a little bit different from one another. So imagine that case where the lines were close but not right on each other. And in this case, we're going to play God. We're simulators, so we're going to know why the two groups are different from one another. In this case, it's going to be because all the units, let's say hospitals in this case, were initially drawn from the same population, but then the probability of getting treatment was a gradient across the quartiles of that baseline spending, or uncompensated care, or Medicaid revenue, or whatever the baseline measure is. So the higher up you are in that distribution, the more likely you were to get the treatment condition, and vice versa. So the obvious result is that we're going to have these two populations that are slightly separated from one another. And all we have to do is wait a little while and remeasure them. And what's going to happen? Well, in a crowd full of statisticians, we know that the answer is regression to the mean, right? We sort of artificially separated the two populations, which were really just one population, by virtue of the treatment assignment mechanism. It got assigned based on level. And so if you just wait long enough, they will all actually kind of go back to that common mean. And now, if you run a difference in difference analysis on this by fitting that linear regression model, And the way people do this is they do linear regression, and they put in a term for the baseline difference between the two, an indicator for being in the post period, and then an interaction between the two. This model is just identified if you have that 2x2 case that I talked about earlier. There's 4 parameters, 4 observations. But with more complicated data setups like multiple time periods, it's not quite that bad. But anyway, the right answer in this little simulation is that the interaction between post and treatment should be 0, because there was no treatment. We just simulated these data, right? Nothing's going on, and yet we have this very biased estimate. So we could match, right? Remember, this population was a bunch of little hospitals. Some of them were treated and some of them were controlled. And if we just pick the units that are closer to one another using any matching algorithm that you want to do. In this case, I happen to be matching on outcomes, but you could be matching on covariates. And as long as those covariates were good predictors of the outcome, all the same things are going to happen. The unmatched cases look especially separated, right? That's the point of matching, is you leave behind the cases that can't be matched because they're not as comparable, and you take only those cases that are in the middle. You get an unbiased difference in difference. So now, because we constrained the two groups to have the same mean at baseline, there was no place for them to regress back to, because they were already at their common mean. So this setup, this simulation scenario, was recommended, was used as the basis for a recommendation that you should match on stuff in difference in difference by Andy Ryan and colleagues in a paper that was published in 2015. And they noted that you get this great, now we've got this awesome unbiased estimate, ta-da, we should definitely match. And my former student, Jamie Daw, who's now on faculty at Columbia, looked at this scenario and said, you know, there's another way that a difference between two groups could arise at baseline. It doesn't necessarily have to be that they were all one population and we just sort of picked off the high and the low and gave them treatment and control. Instead, we could imagine that the hospitals in Alabama and the hospitals in Massachusetts are just permanently different from one another, right? Those are stably different populations with different means. And in this case, if I do the unmatched analysis, don't mess with it, don't match anything, just do diff and diff, the answer is unbiased. But here's the really pernicious part. If I match in this setting, now my diff and diff is biased. I created this bias. It was not there. This was a fine study. Everything was going to be okay. And I created it by matching. And what's really a bummer about this whole setup is you cannot tell the difference by looking at the data in whether the treatment assignment mechanism was the first one, where they're all one population and you just happen to see treatment and control looking different because of that mechanism, or they were stably different populations. As long as the treatment assignment mechanism can see all the data that you can see, you can't tell the difference. There's no way to tell. And in the top one, if you don't match, you're going to have bias. And in the bottom one, if you match, you're going to have bias. Man, this is such a bummer. So we wrote this I wanted to say that these differences look really small, right? These are numerically small differences. And I wanted to reassure you that small differences are extremely important in policy settings. So my most cited paper ever was published 2 years ago. It's got 170 citations, and it's based on an effect size of 1.4%. So small effect sizes are really important in policy because 1.4% of $1 billion federal program is still a lot of money. So we have concluded that matching on levels, that is matching on baseline stuff related to your outcome of interest or your outcome of interest itself, either creates bias or corrects bias, or, I didn't talk much about this, but in the case where the thing that you're matching on is non-time varying, it's stable over time, you can't have regression to the mean, right? So in that case, it has nothing to do with bias. So back to your earlier question about why are there errors, people frequently match on time invariant characteristics. And I don't understand why. Because time invariant stuff gets differenced out in a difference in difference analysis. Anything about the groups that stays steady over time will be differenced out. There should really be no contribution of those characteristics to bias in a diff and diff study. Maybe you can make some argument about variance, but really that time invariant stuff shouldn't matter. So this is really challenging, and so we wrote this really fun sequence of papers. So Jamie and I's paper just came out in HSR. Andy Ryan, who, remember, started this whole thing with his paper a few years ago, was a reviewer and then wrote an editorial to accompany it. And then finally, we didn't actually put this whole story together about regression to the mean being both the source and the solution to bias in these two cases until the response to his commentary. So I think this little cluster of papers was one of the most rewarding methods series that I've ever done because it has big real-world consequences, and it was a neat exchange of ideas between us and the reviewer that actually made the story complete. So it was really fun to work on. There are other folks, so here's that initial Ryan et al. Paper. There's the 3 papers from HSR. A guy named Shabe Ferre has just published a very cool working paper where he works out the theory of all of this and concludes that matching is always dominated by other strategies in diff and diff, and you should just never do it. And then Liz Stewart and her colleagues published a lovely paper which actually gets you out of this whole bind. So the fundamental thing about this phenomenon is that you create a constraint in one period, that is the pre-period, and then you release it in a subsequent period. So you match in the pre-period, and then you can't match in the post-period because you might match away your treatment effects. So you have to just take your hands off and say, I'm not going to match anymore. It's that application and then releasing of the constraint that leads to all of this trouble. So Stewart and colleagues actually developed a propensity score weighting scheme that weights 3 out of the 4 groups, that is pre-post treatment and control, right? Imagine 4 groups, 3 of them towards one of them. So you pick one referent group, say the untreated pre, you weight all of the other populations towards that. Now you can't be weighting on outcomes there, but you can weight on other stuff, and therefore you can apply the constraint symmetrically across that boundary from pre-intervention to post-intervention. And then you get away from these difficulties. So I would say that it took us a while to figure out what was going on with matching in diff and diff, but if you want a way out of it, I would say read the Stewart et al. Paper. I'm going to pause here for questions about the whole matching shenanigans.
You mentioned that your approach is the way out. But that's another assumption that you mentioned earlier, that providers treat the victims and equally important is the victims.
Yes, the assumptions that underlie the use of covariates in any way in this causal inference framework are strong. And I think that is just the bind that we're all in. Liz can't get us out of that. So we have to believe that the covariates are doing important work in some way. They are making the assumption, the causal assumption about counterfactuals more plausible somehow. And because it's an assumption about counterfactuals, it's something we can never empirically verify. We always just have to argue based on subject matter knowledge that those covariates are somehow helping us feel better about the counterfactual assumption. But we can never really know. So yeah, if we have junky covariates, we have junky covariates.
Like that in the sense that, if like 14 people get the treatment and 10 million don't, how do you get such a big control group kind of wash out what happened because of this non-thing?
Yeah, so my colleague Mike Chernew, whose picture you saw a minute ago, often argues that really the exercise that we're trying to do is averaging over sources of error. And then if you can average over enough sources of error, you can get yourself out of all of these problems. I don't know whether he's right or not. I haven't written the papers yet, but we're working on it. There is definitely a challenge for inference in the case where you have a very disparate number of treated and control, especially in the case where you have one treatment unit. So oftentimes in the US, we do state evaluations. So you often have one treated and 49 controls. That's really challenging for inference. But whether that is also challenging for a bias, from a bias perspective, is an open question. Yeah.
So I completely understand your math. I get it, I believe it. I've done enough different diff studies, health policy type studies, that I guess just a few things I don't understand. So for example, we have done matching of EDs, emergency departments, and sub-interventions of them, which is trying to reduce crowding. and we match on something like volume.
Okay.
Low volume ED. You can't compare them, so we match. That's like a time invariant covariate. And you're saying it's got nothing to do with the bias. And yet, no, I agree over time, high stays high, low stays low. You have to match, like within these groups. You can't compare high to low. But I think that does get rid of bias. So there's something I'm not getting.
I should caveat my earlier statement about bias. If there's effect heterogeneity, which I think is the reason that you're matching, you think that effects will be different in high and low volume EDs? Because I would buy a bias story there.
Right, how do I know it's more crowded? You're finding
Or ceiling effects, maybe?
ceiling effects are different.
Sure.
And maybe ceiling effects, so they can go down more, like the crowdedness can decrease more in a high volume.
Yeah. So that may be like a mechanistic form of treatment effect variability that in high volume EDs, there's a bound on how much more crowded they could get, or vice versa.
Like a 10% drop is a lot of people.
Yeah.
And in a low volume, 10% is not as many.
And you just said another word that reminds me of model specification questions. So whether the effect is linear on the additive scale, which is what most of these, or linear on a multiplicative scale, which if you're talking about a 10% reduction, reminds me of a multiplicative scale. And this assumption about a constant difference over time is very scale dependent. So I could buy a lot of stories about either floor and ceiling effects, scale variances, or other forms of heterogeneity across covariates that's different from these extremely simplistic scenarios where everything is super, super clean. So thank you for that, yeah. Okay, that was fun. Let's talk about the second question. So testing trends. How useful is it to test for parallel pretrends? So in the applied literature, you pretty much can't publish a diff and diff without saying something to the reviewers and to your readers about looking at parallel pretrends. And the reason is because of this assumption that the difference needs to stay constant over time. And if you look just in the pre-period, you can get some signal about whether the difference has historically been constant. So I just subtracted those two lines from each other and plotted them. And you could imagine that in the pre-period, you would be interested in knowing whether that has basically stayed flat. And here it looks like it has. So why do we care about whether the trend has been consistent or the trends have been parallel in the pre-period? I think it's because of how the counterfactual assumption, which I gave in this really pedantic way at the beginning, has been described previously in the literature. So my poor buddy, Andy Ryan, here I am picking on him again. This was a paper that was published in JAMA. So this was advice for medical researchers who want to do diff and diff studies. This is not a methods paper, it's just one of those little viewpoints. And they write the crucial counterfactual assumption as two assumptions, which they say are the parallel trends assumption, which is that the trends have been parallel in the pre-period, and the common shocks assumption. And this is where you start to see the influence of the economists on this literature. Shocks to economists are errors, basically, right? Stuff that happens from outside that just impinges upon the system that you're studying and is random and just whatever, a recession happened, right? So if you add these together and kind of squint your eyes, maybe you get back the counterfactual assumption at the beginning, but because it has been split up in this way into two assumptions, I'm going to pick on the parallel trends assumption, and I'm going to pick on it in three ways. My fundamental problem with that assumption is it is not an assumption. Whether the trends were parallel in the pre-period is an empirically testable fact. We have all the, we've got the data. We can just figure it out, right? Second is that when people test that, which they do, right? Because you've set up an assumption that is testable, so of course we're going to test it, right? When people do that test, I'm going to argue they use the wrong null hypothesis. All their tests are exactly backwards. And then third, even if you think that doing this parallel trends testing is a good idea, and I fix up the statistical problem, it is neither necessary nor sufficient to satisfy the actual counterfactual assumption, right? So here's another set of quotes from the literature showing you that people really do get concerned with this parallel pretrends assumption. It is cited often as a thing that you should care about, and it's tested and looked at. Here's how people do that, right? This is the obvious thing to do. If I have set up for you a test about parallel trends in the pre-period, the obvious thing to do is fit a model to the trends in the pre-period and test whether an interaction term between treatment and time is significant. Because that beta 3 there represents the differential trend in the treatment group relative to the control group. And if beta 3 is 0, then the trends are equal in the two groups, right? So the null hypothesis, the way we just sort of always do, but da-di-da, beta 3 equals 0. We're going to test that. We're going to look for evidence against it. Unfortunately, the easiest way to pass this test is just to have low power, right? You can't reject a null hypothesis that you're not powered to reject. So even though on the the left graph, there's a bigger slope difference, the variance is higher, so we can't find it, so we're less likely to reject. So this is the statistical problem I have with this test, and it leads to this funny paradox, which is that underpowered studies always pass because we have insufficient evidence that there's a slope difference. And well-powered studies, eventually, once your study gets big enough, you're guaranteed to fail this test, unless the true slope difference is identically 0, which of course it never is, right? Okay, bummer. However, this is actually not that big a problem, right? We're statisticians. We are not the first people to try to show that something is 0, right? We can never prove the null, but we can rewrite the null. And we can, instead of looking for evidence against a beta 3 of 0, we can look for evidence against a large difference in slopes. So the non-inferiority or equivalence testing framework that has been well published in the clinical trials literature I'm importing that here and saying what you have to do is show me that the size of the violations of the parallel trends assumption is not big enough for us to worry about it. Okay, so a couple complications here. First, now we have to pick that threshold delta, right? We've solved one problem, which is that we've solved the paradox problem. So now our well-powered studies are going to have sufficient evidence to reject those large violations, and we can go on with our lives. So that's great. But we still have to pick that value of the threshold of violations that are big enough to worry us. Well, how would we pick that? Gosh, I don't know. Let's just try a bunch of different values of delta and see what value of delta we can start passing the test at. I'm going to come back to that in a second. If we try a bunch of different values of delta, eventually there will be some delta here on the x-axis that is big enough that any study is going to be able to rule out a delta of 1 million, right? We can certainly do that. In this simulated case, this is due to my student Alyssa Belinsky, a value of delta of 0.7, I don't know what that means, but that's the value where in these data we can definitely rule out values that big. So we could say, I don't know what the right value of delta is, but I can certainly tell you that at an alpha level of 0.05, I can rule out betas or violations of parallel trends that are at least that big. What this should remind you of is that stat 110 exercise of inverting a test statistic to get a confidence interval, right? So instead of using a hypothesis testing framework, what we actually suggest in our paper on the archive is that you adopt an estimation framework, which is to say, estimate how big the size of the violation is and be really concerned with that upper bound. How big do you think it is not bigger than? And then let your readers decide whether that size of violation is big enough that they should be worried. Okay, this is not blindingly brilliant insight. This is all like basic stat stuff. But the number of times that I have seen in the literature a conventional null hypothesis test done and they don't find anything and then they say, oh, I guess our parallel trends assumption is satisfied. I think this needs to be said. The other problem that this test inversion idea has is that it's terribly powered. Right? Proving that things are not big turns out to be quite a lift for your data, especially because, remember, we've taken our study and we've thrown out all the post-intervention data. So we're only working on part of our data anyway. So in this scenario, which again comes from simulations, we have matched the form of the violation to the form of the test. So it's sort of a best case scenario in that sense. We're testing for a thing that has the right parametric form. And with a large violation, and by large I mean as big as your treatment effect. So this is as big as the effect that you can detect with your main study. You only have 50% power to rule out violations that are at least that big, which is terrible, right? So the low power, the problem of picking delta, and the fact that really this should all just be replaced with an estimation with confidence intervals procedure is my solution to the statistical beef that I have. Okay, so beef number 3. This is my conceptual problem with the parallel trends test. What we have in mind when we do that test is implicitly that trends are persistent and that a difference that we see in that pre-period is going to persist in the post-period. Now that idea of persistence is in fact the assumption itself, right? That stuff we see now is going to persist in the future in the counterfactual world. And so this picture, I think, is what we have in mind, right? If I see a difference in the pre-period, it's because in the post-period, and remember, for one of these groups, this is the counterfactual post-period. These are the counterfactual outcomes that I don't actually get to see. That difference would persist. And that if I pass it, everything's good, and that was also going to persist. But the real world, in my experience, doesn't actually look like this. In fact, sometimes these horribly divergent pre-trends would have self-corrected. So is this a good counterfactual? I don't know. Mathematically, the expected change from pre to post in the two groups is the same, right? They both changed 0. But they took very different paths to get there. So the idea that these two work as good substitutes for one another is, I think, a little bit implausible. And moreover, this picture is just a few points from a much bigger graph, which is messy and gross. And are these trends persistent? I'm not really sure. What does it even mean to have a trend with data this noisy? So I think that the focus should be on applying our substance matter knowledge of the system under study to make an argument, a principled argument, for why we think trends will be persistent across the groups that we've selected on the outcome that we care about, rather than doing poorly formed statistical tests on data that may not even have this persistence property. Or we should at the very least have to prove something empirically about the persistence of trends in the outcome that we're studying. So we're not the first people to think about this either. So a bunch of papers have just recently started to pop up in the archive and in the working papers series of the National Bureau of Economic Research for other people who have noticed that doing this test is not a great idea. Pause here for questions about testing for parallel trends. And in fact, I will say that, so this paper that Alyssa and I have written, which is out on the archive, makes the argument that we do this kind of testing all the time when we have some sort of restriction or precondition of our analysis method, like say equal variances, and yet we still formulate it using that conventional point null hypothesis of no difference or no violation, and then go ahead with our standard way of testing things. We argue that all of those tests should instead be reformulated, either using an equivalence non-inferiority framework or the estimation point of view, because it's the phenomenon that we've described here for parallel trends testing also applies to all of the other things that we do as a pre-check on the assumptions or the preconditions of our analysis. So now I'll actually pause for questions. Yeah.
You kind of answered this, but yeah, doesn't switching to estimation land get rid of all of these problems?
Yeah. I mean, I'm a Bayesian, first of all. I should disclose that I'm a Bayesian. So my interest in testing is already lower naturally. And I think hypothesis testing in this setting is just the wrong point of view. Null hypothesis testing is not serving our interests very well here, and we should go towards estimation. Okay, cool. So I have a little time. So I'll get to preview those other 2 research questions that we're working on currently. The first one is developing a very rigorous definition of confounding in different studies. So a lot of our intuition for what the concept of confounding means was developed in cross-sectional studies. So this is the classic diagram of what a confounder is. It is some variable X that is related both to treatment A and to outcome Y. Super standard stuff. But we're not operating in a cross-sectional world. We're operating in a longitudinal world. So now we have outcomes measured at time 1 and at time 2. So now a covariate that affects treatment and outcome 2 and outcome 1, is that a confounder? Well, it turns out that it depends on whether the effect at time 1 and time 2 is the same. So it depends on the strength of the relationship. And moreover, what if the covariate itself is time varying? Oh man, now it gets really annoying. So my postdoc, Brett Zeldo, is actually building a beautiful didactic website that we hope to release to the world soon, where we develop rigorous definitions of confounding in difference in different studies specifically, and talk about the ways that you could address confounding. So very often, I read a paper, and the linear model that people write down for their different regression model is intercept, treatment, post, the interaction, plus a bunch of X's. And we just had a fruitful discussion about why you would care about X's. One of the things that putting those X's in the linear model will not do is fix all of the confounding issues, even if all the confounders are observed, because it depends on whether the effect of the covariates is consistent over time, and also whether the distribution of the covariates is evolving differently in the two groups. So this is work that's ongoing, and I think it's very fun and exciting. And other people have thought about this as well. Again, this is becoming a crowded methods space, and I feel like we're in very good company here. Some of the cool papers that have come out recently are on this slide. I'm very happy to share these with folks because there's a lot of good references in here. All right, question 4, briefly, is this question of stability. So I said that my problem with the parallel trends test is in part about whether the trends are persistent over time. And I think that that requires us to understand something about the longitudinal variance structure that's happening in our data. So a paper that was very influential came out a while ago, Bertrand and colleagues, who said you should think about the longitudinal error process, and you should maybe model that empirically, do an empirical estimate of the variance structure in a longitudinal way, because everyone had been sort of waving their hands and saying AR1, and it's a little bit unsatisfying. For very short time series, which is typically what I deal with in the health policy world, I showed you a time series that was 4 data points long. That's really common. 4, 5, 6, 7. These are as long as our time series are. It's actually really hard to estimate time series variance in the way that the time series people do it, so we got to resort to other methods. And what these plots are meant to illustrate is that it's important to remember, what do we mean by error? It depends on what you've put into the model. So error is what's left over after you've put everything else in the model, right? And very often, what people put into the model are unit fixed effects and year fixed effects, or time fixed effects, right? So what that has the effect of doing is demeaning. That's the unit fixed effects. Now every unit is centered around its own mean. And detrending, that is, you take out a bunch of year fixed effects, which is sort of the national trend in your outcome. And so what's left is down here in the bottom right corner, right? And these trajectories are the variance that's left to do 2 things. 1, identify your treatment effect, and 2, be dealt with as error variance. And I think that it is important to remember that really super tidy, nice, even, smooth plots, once you take out unit and year fixed effects, are just a messy spaghetti jumble. And they importantly do not have AR1 variance structure. So this funky block variance structure is what you are going to get if you take out year and unit fixed effects, because everything's going to be centered around its own mean. So if there's any trend at all, it's going to be centered around 0. So positive errors in the first half, negative errors in the second half, or vice versa, right? So they are going to have this funky block correlation structure. And so I think that this is an interesting and fruitful area of future research to really nail down variance structures. So other people have thought about variance and inference as well, and I want to end there. So thank you very much.